In 1891, a 56-ton flywheel exploded inside a Manchester, New Hampshire mill, hurling iron fragments the size of engine blocks through 3-foot brick walls and across an entire river, killing 3 men instantly with the force of a locomotive crash. This was not a boiler blast or a freak accident, but the hidden threat built into every major 19th century factory, machines that quietly stored enough kinetic energy to wipe out the buildings around them, all for the sake of keeping looms running smoothly. But just how could a slow spinning wheel become the deadliest object in the industrial age, and why did factories risk everything on them? A flywheel in a 19th century factory was more than a spinning disc. It was a reservoir of energy, governed by the laws of physics rather than human caution. The formula for stored energy, 1/2 times the moment of inertia times the square of the angular velocity, meant that every increase in speed multiplied the risk. At standard operating speeds, 30 to 60 revolutions per minute, the rim of a 40-foot wheel could travel faster than a city car, often exceeding 40 miles per hour. The danger was not just in the speed, but in the silent buildup of force. Cast iron, the material of choice, could withstand 100,000 pounds per square inch when compressed, but under tension it failed at less than 20,000 pounds per square inch. When a wheel spun, centrifugal force pulled the rim outward, loading every bolt and joint with relentless tension. A small overspeed, just 10% above normal, could raise internal tension by more than 20%, pushing the iron past its breaking point without warning. Most flywheels were not solid, but were built in sections and bolted together, concentrating stress at every seam. Over weeks of continuous operation, heat cycles and microscopic flaws grew into cracks deep inside the metal, cracks invisible to the eye, undetectable without modern tools. The first sign of trouble was often the last, a sudden catastrophic failure as stored energy released in an instant. In that moment, the flywheel became a weapon, and the factory walls offered little protection. Inside the great factories of the late 19th century, scale was everything. A single flywheel, weighing anywhere from 20 to more than 100 tons, often filled the engine room wall to wall. In the largest mills, some wheels approached 200 tons and stretched 40 feet across, their rims sweeping past stone and brick just feet from where men worked. This was not excess, it was a necessity. Steam engines of the era delivered power in uneven pulses, each stroke of the piston sending a surge through the line shafts. Without a massive flywheel to absorb and smooth these jolts, looms snapped threads, presses jammed, and production ground to a halt. The solution was to build bigger. Heavier wheels could store more energy, allowing the engine to run steadily through minor power dips and sudden demands. Stopping a steam engine meant hours of lost output and wasted coal, so every incentive pushed managers toward larger, heavier wheels that could keep the whole system moving. The economic logic was simple: maximize uptime and minimize costly shutdowns. As a result, the flywheel became the beating heart of the factory, powering hundreds of machines at once through a web of spinning shafts and belts. Every inch added to the wheel's diameter, every ton of iron meant smoother operation and higher profits. But it also meant that when something went wrong, the consequences would not be limited to a single machine. The entire building, and everyone inside it, was tied to the fate of that one spinning mass. Engineering journals from the 1890s read like accident logs, each entry a record of sudden destruction. In Pennsylvania, a flywheel burst without warning, sending fragments of iron through the engine house. 2 workers died instantly. The largest piece, weighing more than half a ton, traveled straight through a 2-foot-thick brick wall and landed over 100 yards away, well beyond the factory grounds. In England, investigators found iron sections embedded in neighboring buildings, some fragments discovered hundreds of feet from the point of failure. The violence was never contained by stone or timber. At the Montgomery power plant in Pennsylvania, in 1916, the disaster unfolded in a matter of seconds. As the engine oversped, the flywheel tore itself apart. One fragment, more than 200 pounds, shot across the property, ripped through a tin shop, and buried itself in a sandbank 600 yards away. Another piece struck a building 500 feet from the engine room, while brick streets and telegraph poles fell in the path of the debris. The entire plant was left in ruins, but no one died only because the accident happened at night. A historian describes these events as a pattern, not an anomaly. Dozens of incidents from the 1880s to the 1920s show the same signature, catastrophic failure in less than a second. Iron fragments launched at rim speed, and destruction that reached far beyond the engine room. The records make it clear, when a flywheel failed, nothing within a football field's length was safe. Containment was the first answer engineers and insurers turned to, but the results were sobering. Timber and steel housings were built around some of the largest flywheels, and they were tested in controlled blasts and in real-world failures. These barriers could stop fragments weighing up to 300 pounds, enough to catch minor debris, but not the main threat. When a wheel burst, pieces over 1,000 pounds still punched straight through, leaving walls and containment splintered in their wake. Some factories dug pits beneath the engine room floor to channel the force downward into earth and concrete. It helped, but only for fragments that happened to fly low. Others tried reducing speed. Cutting the wheel's revolutions by 1/4 could nearly halve the stress on the rim, but this also meant less smoothing power for the machines above, and managers worried about production losses. Insurance companies kept careful ledgers. After a major failure, the cost to rebuild an engine house often soared to 5 times the value of the destroyed flywheel itself. Yet, with every disaster, the underlying design persisted. Insurers raised premiums for uncontained wheels, nudging owners toward thicker housings and pits, but these measures only bought time. The economic pressure to keep wheels spinning, and spinning fast, outweighed the lessons of containment tests and the warnings in the ledgers. Incremental fixes could not match the scale of the hazard. The flywheel remained at the heart of the factory, its dangers only partly veiled by wood, steel, and earth. The arrival of distributed electric motors changed the factory floor almost overnight. Instead of relying on a single flywheel weighing over 100 tons, power could be delivered by dozens of smaller motors, each assigned to its own machine or section. This new approach cut the largest rotating mass in a converted plant by more than 90%. Maintenance logs from the 1920s show downtime plummeted, thousands of hours saved each year, as machines could be stopped or serviced individually without halting the entire mill. Engine houses shrank or disappeared, and the risk of a single failure destroying an entire complex faded into the past. The relentless pressure to keep one giant wheel spinning was gone, replaced by a network of motors that brought both efficiency and safety. Insurance ledgers from the 1920s tell a clear story. As factories switched from giant flywheels to electric motors, insurance premiums fell, sometimes by half. The reason was simple. The risk of a single failure destroying an entire plant had vanished. Instead of one machine holding enough energy to level buildings, each motor carried only the power needed for its own task. When a motor failed, the damage was confined to a single workstation. Catastrophic bursts that once sent debris hundreds of yards became a thing of the past. Repair costs dropped, and the sweeping losses from flywheel disasters faded from the books. For the first time, safety and profit aligned. The era of the massive flywheel, with its hidden dangers and outsized risks, ended not with regulation, but with a new technology that made the old hazards obsolete. Today, most industrial risks hide behind algorithms, not iron. Yet every leap in efficiency carries silent trade-offs, sometimes measured in human lives. The lesson remains. Power, unchecked and unseen, still demands respect. Every system we build is only as safe as the dangers we are willing to confront. Thank you for watching.